So for this project, we're trying to get the dog Lassie from point A to B in the fastest way possible. A couple of variables that we don't know. R is the running speed, which would be from point A to D, and S is her swim speed, which would be from point D to B or C to B if she ran all the way from A to C. A couple constants are the Z value, which is the distance that Lassie would run on land, and the X value, which is the distance that she could swim. If a couple conditions, if R equals S, as in her running speed equals her swim speed, we can assume that her length that she runs on land is very, very short, making Y very, very large, and she would swim most of the way almost directly from A to B. If her running speed is a lot larger than her swimming speed, then we can assume the Y to be very small, and she will run mostly on land from A to C. If her running speed is less than her swim speed, then we can assume that there is no solution because she would just swim the entire way then straight from A to B, and the shortest distance and time would be the Pythagorean theorem of X and Y to get the distance from A to B. So to solve for the least amount of time to get from point A to B and the least amount of distance, we set up the equation T of Y equals Z minus Y over R plus the square root of X squared plus Y squared over S. And then as you can see, we rearrange that to Z over R minus Y over R plus 1 over S times the square root, or times X squared plus Y squared to the 1/2. And since Z and R are constants, Z and R can also be eliminated because when we take the derivative of constants, they turn to 0. So you can see in the first derivative, it equals negative 1 over R plus 1 over 2S times X squared plus Y squared to the power of negative 1/2 times 2Y. And also, taking the derivative of X squared is also equal to 0 because X is also a constant. So when we give that a 0 set, you see that we rearrange the equation all the way down to Y equals S times X over the square root of R squared minus S squared. And you can see from this, kind of going along with the assumptions at the beginning, that if R is less than S, there is no solution. And since her swimming speed is larger than her run speed, she would just run straight, or she would swim straight from A to B. And if R equals 0, it's also no solution. Therefore, we assume from the answer of this derivative that her running speed is larger than her swim speed. So next we have to prove that our first derivative will yield us a minimum time value, not a maximum. So for that, we performed a second derivative test where we took the first derivative, as you can see, took the second derivative of the first derivative, got 1 over R to equal 0 because R is a constant. And then after simplifying, we ended up with X squared over S times X squared plus Y squared to the 3 over 2 power. And if X and S are positive values, which they are, then this would always yield a positive value for the second derivative, which would make this concave up on a graph and would make it a minimum, which confirms that the equation will give us the minimum time of Lassie to get from point A to point B.
In part 2, our goal is to find the relationship between the distance y and x. We'll find the relationship by using the equation solved for in part 1, which was y equals sx divided by the square root of r squared minus s squared. In the table, we are given both running and swimming times for Elvis at 20 meters and 10 meters respectively. The first thing we did was solve for the r and s values by using the distance and times given in the table. The r and s values represent the running and swimming rates of Elvis. For example, for the first set of times, we first solved for r by taking the distance, 20 meters, and dividing by the time, 3.20 seconds, to get a running rate of 6.25 meters per second. Then we solved for s by taking the distance, 10 meters, and dividing by the time, 12.13 seconds, to get a swimming rate of 0.82 meters per second. To solve for y in the first set of times, we plugged in the r and s values we obtained into the equation. After plugging in and solving for the equation we found in part 1, we calculated a value of y equals 0.132x. We then did the same thing for the next 4 sets of running and swimming times. After finding the value of y for all 5 equations, we then added up all of our y values and divided them by 5 to get the average relationship between distances x and y, We found a relationship to be y equals 0.139x.
In part 3, we analyzed 35 pieces of data from Pennington's experiment to test Elvis's running and swimming times to retrieve a ball in the water. And after plotting these on a scatter plot, we see that his line of best fit is y equals 0.1951x minus 0.3102. And then we can also create a plot based off of the equation we get in part 2 to determine Elvis's predicted values. And what we get is a line of best fit of y equals 0.139x. And if you compare these two scatter plots, you do see that the graphs are quite similar to each other. And from this, we can conclude that Elvis the dog can indeed do calculus. But when we take these two graphs and plot a residual graph, we can see that for distances shorter than about 10 meters, it's easier for Elvis to optimize his retrieval time because it is easier to judge. But this makes sense because as you increase the distance, it is harder to tell to the naked eye how far an object truly is. And there are a few outliers that we do see on the graph, but this makes sense because this is just due to Elvis's ability to visually see and judge how far the object of retrieval is.
For part 4, we address the limitations that occurred in this project. One limitation was inconsistent data. The owner did not measure the precise distance each time, but rather guessed or estimated when the dog swam or ran. Another limitation with the data was the assumption that the dog completed it or ran and swam at a constant rate. The dog might have ran faster and swam slower, or vice versa.